reasoning. Use inductive reasoning to find the pattern. Make a reasonable conjecture. All right, we're asking you just to find the pattern. If we look at the list of numbers is increasing. So it's increasing by a multiple of 3. So if we look at the last two, 70 to 91 has increased by 21. So that means 21 will, if it's a multiple of 3, what comes after 21? 24. What comes after 24? 27. What comes after 27? It's going to be 30. So once you identify the pattern in the early part of the list, you can carry it out in the sequence. So we're going to have 91 plus 24 is going to be 115. And then we have 115 plus 27. I have 142. And then 142 plus 172 is going to, plus 30 is 172. 2 patterns in a series or in a sequence. If you look at our numbers, they go high, or they start low, then they go high, then they go low. But if we skip, here's what you're going to notice. We have 15 to 17, 17 to 19, 19 to 21, 21 to 23, 23 to 25, which means that 25 will go to this space right here. And those numbers are increasing by a pattern of 2. So 25 plus 2 is going to give us 27. Now, in the next pattern, we have where it starts off high and then goes low. So 28 to 25, 25 to 22, 22 to 19, 19, 16. And then it's going to include the number 16 minus 3. So that's going to be, because our pattern here was negative 3. So 16 minus 3 is going to be 13. And then 13 skip minus 3 will be 10. To find the pattern, then make it a reasonable conjecture for the next item in the sequence. Okay, so number 3 is pretty easy. If you have an empty box, so let's see, you have an empty box, and then you have a box where the pattern is even, but it's empty. So that means we're going to have a pattern where all the squares are empty. So in this one, number 3, we didn't even have to consider the second or the fourth. Then we have number 4. So this one is just the patterns, and this one's kind of easy to look at as well. So when let's use a highlighter. So right here you have a 6-sided shape, and then becomes the outside shape. And then whatever is next after that, you have a 3-sided shape, and then it becomes the outside shape. So whatever is inside the shape will become the outside shape. So let's think of it like that. If I have an oval here, the oval becomes the outside shape. And then lucky for us, we have this, I guess, like cross. So that cross is going to become the outside shape. And then what's left to determine is going to be inside shape. If we look at what's following, remember whatever is on the inside becomes the outside. Then we get this trapezoid. So the trapezoid will be inside. And there's our pattern. Let's use the color to highlight the differences. And 6, say use a counterexample to show the statement is false. A counterexample is a general claim, and all you need is one case. or does not hold true, that makes it the counterexample or a false claim. A number is divisible by 9 if the last 2 digits are divisible by 9. All right, so let's produce some numbers that have 2 digits, 0, 9, 1, 8, 27, and 36. Now, it says a number is divisible by 9 if the last 2 digits are divisible by 9. We're not making a 2-digit number here, everyone. We're making a 3-digit number. And the least 3-digit number we can make is with a 1 in the hundreds place. So now let's see if we can find a false. So it's saying that all these numbers are supposed to be divisible by 9 if the last 2 digits are divisible by 9. Is 0, 9 divisible by 9? Yes. But is 109 divisible by 9? No. You get 12.11. Let's see. Is 18 divisible by 9? Yes. But is 118 divisible by 9? So in this case, we know that first example is false. Is 118 divisible by 9? So I get 13.11. So this is also another false claim. 6, when an odd number is squared, I have a list right here of odd numbers, 1, 3, 5, 7, 9. Any number that ends in those numbers is odd. So go back to number 6. When odd number is squared and divided by 2, the result will be a whole number. So what I've done is I broke down the steps. We have to pick an odd number. So the odd number we're going to pick is going to be, let's just use 5. So the odd number is squared. We have that. So 5 squared equals 25. And then it says that number is divided by 2. So 25 divided by 2. And it says that the result will be a whole number. A whole number is a number without decimals or a fraction. So a whole number is going to be 25 divided by 2, which is 12.5. So this right here is your counterexample. Remember, to have a counterexample to prove a statement is false, you just need one item to show it's false. About the rule that states a number you're selected to the final answer, try to prove your conjecture by using deductive reasoning. Okay, so whenever you have a rule in math, especially at like the college level, we're talking about like an algorithm, and we typically have the use of a variable. So let's just select a number and then let's try doing it with a variable. All right, let's select a number. Let's use 5 again. So select a number 5. And then 5 is multiplied by 9. That's going to equal 45. Then add 21. 45 plus 21 is going to be 66. And then we're going to take that number and divide it by 3. That's going to be 22. And then subtract 3 times the original number. This right here is the original number. So subtract 3 times that original number. So 3 times 5. 22 minus 15 is going to give me 7. So my result is 7. So let's try this with a variable to make it a little bit more challenging. So x is going to equal x, and then we're going to multiply x times 9, which is going to give us 9x. Then we're going to add 21, 9x plus 21. And then we're going to divide by 3. So 9x plus 21. All of this divided by 3, which ends up being 9x divided by 3 and plus 21 divided by 3. So I get 3x plus 7. And then it says to subtract 3 times the original number. This is my original variable, which we're going to call our number, right? Well, it's an unknown number. So we subtract 3 of the x. So then when you're subtracting and they're on the same line and they have opposite signs, they go away. So my answer here is 7. So it works with variables and numbers. A 7, I thought we were looking at 6. Let's look at number 9. So this is called a factorial. So a factorial is a exclamation point after the number. So let's expand the factorial. So it's basically like a counting number. So if I say I have 1 factorial, that's just 1. And then I have 2 factorial, we're gonna expand it. And we're expanding so that you understand that 1 factorial is just 1. So 1 factorial is equal to 1. 2 factorial is equal to 2 times 1, which is equal to 2. Let's pick something larger. We go all the way down to like 5. I'm going to go right here to 5. 5 factorial is equal to 5 times 4 times 3 times 2 times 1, which is going to be equal to 120. Now, the difference between 6 factorial and 5 factorial is we're going to take all the numbers after 6 and still multiply them by 6. That's a 5, by the way. So that includes the numbers from high to low. So you're going 6 times all of these numbers, but right here, right? So if I say that the difference between 6 factorial and 5 factorial is that 6 factorial just includes the number 6 and all the numbers that follow that were included in 5 factorial. So that means if I list all the numbers before 6, 6, 5, 4, 3, 2, 1, it's basically like saying 6 times 120, which is going to be equivalent to, let's see, use our calculator, 6 times 120 is equivalent to 720. Or if I wanted to do the long way, 6 times 5 times 4 times 3 times 2 times 1. So 7 factorial is going to be 7 times 720. Let's see. So the total for 7 factorial, I'm just using my calculator, is going to be equal to 5,040. So that means 8 times 5,040. That's going to give us 40,320. And then 9 times 40,320 is going to be 362,880. 10, 11, 12. There's a couple more that follow, but you'll figure it out. Use inductive reasoning to make a conjecture about the next 3 sums, then perform the calculations to verify your conjecture is true. Number 1. Number 1 says 1 is equivalent to 1 over 1 times 2. All right, so if we look at the left-hand side of the equation, and what I mean by left-hand side, you have an equal sign, so this is the left and this is the right. Let's look at just the left-hand side of these equations. See how they're just increasing the denominators for every pair of numbers that exist? Okay, so you're not having to expand the numerator and denominator. But what you are having to solve for is adding them all together. Yes, you can use a calculator to add them all together, but there's a pattern here. And the pattern that exists is going to be between the numerators on their own and the denominators on their own. So let's talk about a fraction. A fraction includes a line. So you have a numerator, and then you have a denominator. A numerator is on the top, denominator is on the bottom. I am not going to concern myself with what's happening over here. You can if you want. That's going to just take a little bit longer for your homework. I'm going to go ahead and concern myself with what's happening here. So again, if I'm looking at numerators, just the top number, let's look at a pattern that we can develop. And then if we're looking at denominators, let's look at the pattern we can develop there as well. So I have, again, a numerator over a denominator. My numerators in green are 3, 5, 7. So if you look at those, 3 plus 5 plus 7, we're increasing these by 2. So let's figure out the next 3 numerators in the sequence. So 7 plus 2 is 9, 9 plus 2 is 11, 11 plus 2 is 13. Now let's figure out the denominator. The denominator here, our pattern is 2, 3, 4. So it's adding by 1. So you're adding by 1. So let's determine the next 3 denominators. So I have 4 plus 1 is going to give me 5. I have 5 plus 1 is going to give me 6. And I have 6 plus 1 is going to give me 7. So I'm going to go ahead and put a box around the answers. Let's make it something bright. So your first solution is 9/5. Your next solution is 11/6. And your third solution is going to be 13/7. A little bit more specifically. So in the example here, we have, you can apply a general rule to a specific situation as deductive. Here's the example. Experts say opening emails from unknown senders can give you a computer virus. Jane opens one from someone she does not know. So therefore, Jane will get a virus. That's deductive. Then inductive means that you take something specific and you generalize it. So, but again, the generalization is not guaranteed. The first 3 games of the year, the parking lot was packed with tailgaters. Conclusion, next week, we'll need to leave early to find a spot. It's not guaranteed that there's going to be tailgaters, but that's an example of inductive reasoning. The type of reasoning used is inductive or deductive. So the first 3 games of the year, the parking lot was packed with tailgaters, so we'll have to leave an extra early to find the spot. This is going to be inductive. This is just like thinking through the real world scenario. Next is going to be experts saying that opening email attachments that come from unknown senders is the easiest way to get a virus on your computer. Shauna constantly opens attachments from people she does not know, so she'll probably end up with a virus on your system. I would consider this deductive. So you took a general situation, you applied it to a real world situation.